At that moment, physicists say the electron is a particle and it's a wave. And immediately the experimental physicists take a beam of electrons, send to a double slit, and look what happened after the first skin. What they got, not two places where the electron arrive. They are no particle, but many. They are wave.
They're a wave. Okay.
This was the demonstration that the electrons are wave. The electrons are particles, are a wave. This is the huge thing of this experiment today. No?
Yeah. I mean, what's confusing is how's it both?
Oh, the best answer is, I don't know. However, now the physicists have idea about that. Then, basically, the thing is this way. All the quantum particles are at the same time particle and wave. The real difficult thing is a wave of what? For example, when I speak, I produce a pressure wave in the air.
Mm-hmm.
I write to the microphone, move a membrane, is translated to electricity. And then when you podcast, you emit electromagnetic wave. Then one light is electromagnetic wave. My voice is pressure wave. If I hit the table, I have a mechanical wave.
Okay.
Then what kind of wave is the wave that is with the electron? The answer is there are many possible answers. Physicists, we don't agree in what is the nature.
Okay.
Some physicists say it's a real wave. Other physicists say it's a probability wave. This is the more common answer that you listen, more or less in this way. In the second screen, arrive a probability wave. Where the particle arrive, the probability of the electron is very high. When the particle don't arrive, the probability to find electron there is very low. The collection of all this probability is the wave that comes with the electron. Other people think that the wave is just math, don't exist. It's a good way to calculate. What all the physicists agree is that the math is very good.
Mm-hmm.
Permit to predict what will happen with the electron or with any other quantum particle. Then any particle is a particle and it's a wave, but the nature of the wave is not clear. The more important thing is this. Any quantum particle is a particle because, for example, an atom is a quantum particle. It's very small, but it's localized. An atom is here, it's not very far away. Everybody has the idea that the atom is very small. They are particles. But the atom is also a quantum particle. This means there is a wave associated to the atom. The nature of the wave, there is no agreement on that. But there is a wave. And you can calculate this wave using a Schrödinger equation. This is the actual situation about the particle-wave duality of quantum particles.
Okay.
There are many properties of the quantum particles. Some of them are famous on the internet. For example, the more famous one is that the quantum particle can be at the same time in two places.
Right.
That's an entanglement, right?
No, exactly.
Okay.
Entanglement is that the two different particles get entangled. This another thing is called superposition principle. And one of the ways, are many ways to present this, but one of the ways that the particle can be at the two places at the same time, and the best example is the double-slit experiment. The idea is the following. Using a quantum particle, let's say electron or a photon. This is very interesting. Newton's thought that the light is made of particles. Thomas Young demonstrated with the double-slit experiment that the particle is a wave. Now we know that they're both, no?
Right.
Then Einstein and another guy called Planck from Germany, they show that the light really is made of particles. These particles are photons. Then I can shoot the double slit with photons or with electrons. Both are quantum particles. And I get, after the two slit, because are quantum, many places where they are right, not two, then are wave. The question is, for which slit the electron pass? Or for which slit the photon pass? Well, if you know, these are experiments that demonstrate that. If you know for which slit the photon pass, the interference pattern disappear and appear two places.
So the waveform collapses.
Exactly. It's enough that you know that pass to one slit and the interference disappear.
So, okay, so let me get this right. So if you know which hole, which slit that the, did you say photon?
Or electron.
Or electron. If you know which slit it was basically shot at, you know it when it arrives on the second screen, it comes out in two spots.
Exactly.
Okay.
We'll put a visual
So
show notes.
Exactly.
So if you, okay. Earlier you said that they're both, and when you shoot it through, it becomes a wave. But if you know which hole it went through, then it becomes two.
Yes.
Well, that would infer that the photon or the electron knew that you knew. Is that right?
Well, this is this is the kind of thing that you listen in internet. But no, when I say, if I make experiment to check for which slit it pass, for example, it's very easy. I close one slit. If I close one slit, appear a single spot here.
Right.
Only when I open the another one, appear many spots. Why? Because I don't know for which one of the two the photon or the electron pass.
Okay.
Let me say how I can say this in another way. Oh, we was talking about superposition principle. What happened in there is that the electron or the photons are quantum particles, then can be in two places at the same time. And then what happened with the photon is that it passed through the two slits at the same time.
Okay.
And this is why you see the interference pattern.
Okay.
Only when you make something that only can pass through one slit, the interference pattern disappear.
Okay. Okay.
And there are many ways to do this. Not only just closing one. This is the simple one. But if you send electron, you can look with photons for which slit the electron pass. And this is enough to disappear the interference pattern. Then,
No, go ahead.
no,
Yeah.
the more important thing for what I want to say is the following. We are talking that there is a wave associated to the particle, and that the quantum particles have several very real strange properties. For example, can be in two places at the same time. Quantum particles. But there are particles that are not quantum. Do you know why?
Not a clue. Why?
No. Do you know any particle that is not quantum?
No.
Yeah, you know. A bullet,
A bullet. Okay.
Oh,
So yes, we do know.
a rocket,
A rocket. Okay.
my body, your body,
Mm-hmm.
are not quantum. We say these are classical particles, are described by the Newton's law.
Okay.
How I know that my body is not quantum as a whole? Oh, because I cannot be in two places at the same time. This will be very, very good to be able to be in two places at the same time, but I cannot do it.
be handy.
Yeah.
Have you been able to do it?
No, I've never been able to do it. No.
Nobody has been able to do it. Then the real thing that we don't talk about is how we know that we are handling quantum particle. What is a quantum particle? Is a bottle a quantum particle or not? And it's like say, is there a frontier between the world of the small things and the world of the big things? Big things are classical. My body, a bullet, a train,
Mm-hmm.
a car. All of these, you don't have to study quantum mechanics. With classical mechanics, you solve this, you can predict where it will go. I say a missile and will hit my enemy, something like that. No, no quantum for anything. But the small things are different. And the difference, the real thing that made the difference is that there is a wave associated to the quantum particle. And there is no any wave associated to a classical particle.
Okay. Okay.
Nobody talk too much about this because we don't know if the frontier exists, and if it exists, where it is. For example, there are physicists, very famous one, first caliber, that think that there is a wave function, there is a wave associated to the complete universe. If this is the case, the complete universe is quantum. And you can use quantum mechanics to study the complete universe. And there are very, very good studies about the universe in this way. The people that think that teleportation, have you ever heard of teleportation, that you can just from here to there go instantaneously, or there is this kind of thing that the people really love, internet, are cool.
Yeah, it's cool.
But nobody have observed this. Never. The physicists that believe that the universe have a wave function, they can say, oh, yeah, this will happen. There is a problem. Nobody have observed this. The question is, why?
Okay. So tiny, micro. Okay. Has a wavelength. Then we become, what did you call it?
Classical.
Classical.
Exactly.
Okay. So we get bigger, classical. And then the universe, which is bigger than us, the universe also has a wave. So as small, big, bigger.
Okay. There are very good physicists that believe that.
Okay.
They have to believe that we are also quantum.
Okay.
Yeah, I was going to say, like, classical objects have quantum mechanics in them, right?
Well, there is a tendency that say quantum mechanics is the reality. The classical mechanic is like an approximation. But look like it's not in this way. There are things that are really quantum, and there are things that are really classical. The difference is that one are very small and another are very big. The universe, experimentally, with observatory, is classical. Nobody has seen a star in two places at the same time,
Right.
a planet at two places at the same time. This never have been observed. However, if there were quantum, it is possible. Then teleportation. Teleportation only happens between quantum entities. If we are not quantum, teleportation of human never will happen. Aliens cannot come to the earth by teleportation. If I listen this, I say, probably the guy drink too much.
Right.
But,
Okay.
But there are good physicists that say, no, we don't know very well now. If you give me some money, I will figure out. And if my army know how to teleportate things, it can put a tank in your back
Mm-hmm.
like this and we win the war. Then the army say, better, let me give a little money of this crazy guy. Maybe he's correct.
Maybe he'll figure it out.
And the guy will have money. And I that think that this is impossible, I will not get it. Then there is some incentive to believe that everything is quantum. Now, this is the actual situation. I have my opinion. Then in some moment, you give me a chance and I will tell you my opinion.
Absolutely. I was just about to ask you what your opinion was, but I'll let you get there.